Yeah, hello everybody. Last but not least, glad to be here again. My name is Nikita Fuchs. I work for Eternity since around 6 years. I'm doing engineering, also helping out different other departments. My background is in business and business informatics both, so I know a bit of both sides. Therefore, not involved too deep in core tech technology in Eternity. But more or less, yeah, assisting engineers and yeah, doing some of the engineering myself. And every time, yeah, I'm here in the conference, by some random chance, there has always been some interesting involvement going on in our research and development that we sometimes do, which I would like to definitely present you today. And yeah, to the viewers watching on video, maybe have a thought or two about, because this is a very interesting topic. The other week, Julie, our lead manager at Eternity, called me up when I actually brought my car to a workshop, and he said, I've got somebody on the phone. They're a big conglomerate. They would love to do some trading and smart contracts with their consortium, but their biggest issue is basically that they don't like it that all the balances of tokens are always public. So they would like to make tokens represent shares, and thereby kind of like allow the partners to do trading, like you know, on the DEX, but they would love to have this data private. So that's of course one of the biggest issues since the token craze of 2018. That has always been. Many of my partners and clients who I worked for always had inquiries for this very use case, but it just didn't work out because the biggest manko was always they required privacy, which of course is not the case for things like token balances, because you have trust through transparency and replicability in smart contracts, obviously, which of course brings in lots of issues along with it. In DEXs, people always hate it when there's front runners. Basically, they see what you're about to do, the trade that you're about to execute, and they front run it and basically gain some profit out of it, yeah, to your disadvantage. Obviously, criminals know how much money you have in the worst case, right? And criminals and governments, they have like very easy ways for installing surveillance on you. And since many years, there has been in cryptography, there has been some work being done on maybe how one could find a way around it. UTXO coins like Bitcoin saw related projects like Monero and Zcash popping up, basically hiding these operations that happen whenever you do a transaction and you want to redeem this UTXO that you received to do another transaction. But this was never really doable properly in smart contract technology. And one field of cryptography that tried to tackle that was the homomorphic encryption. And that's really interesting. It almost sounds like magic. So homomorphic encryption allows you to perform mathematical operations on encrypted numbers without having to decrypt these numbers actually. So you can imagine it like you would give that guy 2 buckets of colors, and he would be with his gloves in that box, just mixing them around and not seeing what he's actually handling there. He could think, yeah, that's maybe a bucket of color, but he would never really know, right? So whenever you're doing some homomorphic mathematics, you never see what you're actually processing there. You just know the operations that you're about to perform. So base yourselves. This would be kind of like the formal depiction. So you have an encrypted number A and you have an encrypted number B, and adding them is the same as basically, yeah, having them off on their own. So what people came up with then eventually were homomorphic encryption libraries and algorithms. Not too long ago, we also in the business development team were contacted by a company who implemented that in library and started to kind of like go to EVM-based chains and all the other protocols trying to sell their solution, basically implementing homomorphic encryption for their smart contract protocols. And the vision here is that basically you as a client, you have the key of the server, so it's your key, and a server, so speaking about a client-server architecture now, not blockchain yet, and the server would have a key which belongs to you, and then basically you can encrypt something for the server, and the server can perform arithmetical operations on it, not seeing the values, returning you the result, and you can decrypt it, basically. The very important thing to know here is that these keys that the client and the server has are related to each other. So just keep that in mind, and just for a little bit later. And maybe you will get where I'm going already. But also good. If you look at the implementation, so non-techie people just focus on the underscored values. So basically, we would have keys in this context. We have the client key, we have the server key. We have some clear text values. This would be 1344, 5, and 7. And we encrypt them. Basically, so from clear A, we create encrypted A, encrypted B, and encrypted C. And then on server side, we would then perform various mathematical operations with these encrypted values. But just note, here the server is just setting the key which belongs to him from that couple. So this will be interesting in a couple of slides. Anyways, following along, we have 1344 times 8, and we get that result. We can perform, for example, multiplication. The second thing is bit shifting, typecasting. Here we perform the min operation, basically take the lower number of them both, and here's always the kind of like clear equivalent of the mathematical operations, and a line below, there's always the encrypted ones. And the last operation is basically a bitwise AND. 7 bitwise 1 is equals 1. And that slipped a little bit. Basically, we're sending the encrypted results back to our client, and down below we see we decrypt with our key, the key that belongs to us, and we can basically see that the clear result equals 1. Okay, so far so good. So, yes? Testing, testing. Okay. So, in a client-server setting, yeah. Sorry? Oh, okay. Was it jamming? Okay. Anyways, in a client-server architecture, this seems all very fine. So basically, we would be able to send somebody and perform some operations on it. Let's imagine we would be a client of a bank. The bank gives us basically the start amount of our account by the beginning of the year. And whenever we confirm it, and whenever we want to withdraw some cash, then we could basically homomorphically, encryptedly withdraw cash from our account, and the bank would not know the amount all the time. And then by the end of the year, we would basically reveal it. But the bank could be sure that we would never be able to withdraw more than we actually own. So right, sounding super interesting. Now the question is, all right, if we have basic mathematical operations, how do we implement this into smart contracts? Because that should be possible, right? So in a token, we also have like multiplication, addition, division maybe, or whatever. Basic mathematical operations in a token contract. And then finally, it would be possible to have token contracts with built-in privacy where nobody would be able to see each other's balances, right? Yeah, but is it? Yeah. So let's take a look actually at how these kind people that we made recently who presented this library that I just showed to you, how they are pitching this vision to the public, because they made an implementation for the Ethereum protocol. So I had it open actually. Yeah, it's a bit weird with the second screen here. Where's the mouse? There we go. So this is seemingly an implementation of fully homomorphic encryption into an Ethereum virtual machine where you have number types which are homomorphically encrypted. And at first glance, it seems that you can easily send tokens to some other person. The amount would be encrypted, and its new balance of that other person would be encrypted too. Let's go.
Hi, my name is Rand. I'm the CEO here at Zama, and today I would like to show you our homomorphic EVM smart contract capabilities. We've implemented a set of precompiles that enables you to have those FHE uints as a new data type in Solidity on which you can do encrypted arithmetics on-chain. For example, if I have an ERC20 contract and I want to protect the balances, I would replace the integer by an encrypted integer in the balance here. And then for the transfer, I would have an encrypted amount, do an encrypted require check, an encrypted addition, and a homomorphic subtraction. If I want to allow specific users to view the balance, I can define all the access control logic of who can decrypt which value that's on the blockchain simply by writing Solidity code. In this case here, just enabling the user to see their own balance, but nothing else. I'm going to compile that. I'm just using the traditional remix tools, nothing new here.
So that was the core promise. Basically, you would be able to decide who would be able to decrypt the previously encrypted value, which kind of like does not really correlate to what we just heard, what they promised and how homomorphic encryption works when you have two private keys, two keys that are basically correlated to each other, right? So I can encrypt something for somebody to perform operations on, and he then produces data which I can decrypt. But listen to what he's saying.
I'm going to deploy it to the Zama testnet using MetaMask. Contract is deployed. I'll just copy it. And I'm going to be using Zama's test web app, pasting the contract address here, confirming. You can see the contract has no tokens minted yet, so I'm going to go ahead and mint 2 tokens. What happens behind the scenes is that I will actually encrypt the value 2 using the network's public key and produce a zero-knowledge proof that I know the value I just sent to the network. This is important for security reasons to avoid people decrypting arbitrary values. Transaction is validated now. If I refresh, I can ask to see my own balance, popping MetaMask request to confirm decryption. We integrated everything into MetaMask to make sure that the user experience is absolutely seamless using MetaMask snaps. You can see here that I've got 2 naras in my balance.
Okay, that should be it for now. So where do we see collisions with like the core principles of homomorphic encryption that we just saw in this library and the context that we have in the smart contract? So the issue here is what he promises is basically that I can encrypt some number. The smart contract will perform an operation on it, and encrypt it to basically a value which then only some other person can read. But that's not how homomorphic encryption works, like as we just saw. So what one would end up doing, actually, when not faking it, is everybody then could have the possibility to decrypt the homomorphically encrypted data that is on-chain. Because as we learned, you encrypt something for somebody to perform operations on, and he can perform these operations only knowing who would be the one to read the results, essentially, right? But if you just perform an addition to somebody's, let's say, balance, which was the only thing that you just saw in the demo, you don't have like the key of this person. And even if you would have it, then these mathematical operations would not be possible, because then you would try to run them, these homomorphically encrypted operations, on two different users' keys. And that would not work. So after digging around in the research that they have conducted in this field and others, the problem basically boils down to homomorphic encryption working very well if you're in a one-to-one relationship. But in a blockchain, we are in an N-to-one relationship. Basically, you have tons of users, right? And all their data needs to be compatible and interacting with what is on-chain. And that's basically one. So digging around and digging around more, it boils down that their solution, basically, whenever you want to read the data, you send a signed request to their nodes, and the way they store the data that you homomorphically encrypt using some non-standard way, which they implemented in MetaMask here, they have a way to decrypt it under consensus and re-encrypt it again for your key. So basically that the transfer of the data itself is safe, right? But so not everybody is able to read everybody's data, which would be then encrypted for the same key on the protocol. They are faking the encryption, the first encryption of the data, which is then stored on a blockchain, have basically a consensus under all these nodes, have a threshold decryption mechanism in place. And they decrypt that data, which kind of then is a backdoor for it, because at some point, at least some of these trusted nodes will know about like the raw data, and then it gets encrypted for your key, basically. So this kind of like can work. So, but the biggest downside to that is not only it's kind of like having a backdoor, like how would we facilitate distributed threshold decryption, because you cannot rely on these parties to always be available or just active or not leaving the network, for example, right? And how can you make it trustless, basically, because you're trusting these people with decryption key parts here. Or maybe we will have better algorithms someday, right? So yeah, unfortunately for now, homomorphic encryption is not a real option for truly decentralized, trustless blockchain protocols. But we will definitely keep pushing for this and see what's on the verge of the research in that case. And maybe, hopefully, one day we will have something very cool. Thank you very much.